Hi, welcome to my video. In this video, I want to talk about the radioactive decay law and the other parameters associated with it. So you probably already know that radioactive decay process is a spontaneous process in which a radioactive sample undergoes radioactive decay. Now, there are different kinds of radioactive decay processes which I have discussed extensively in my previous videos. For example, alpha decay, beta decay, gamma decay. And they're all different from each other because they emit different particles. They happen for different reasons. However, there is something very common between all of these processes, that is the mathematical expression which tells us how the number of particle changes with time is something which is common between all of them. And that is given by the radioactive decay law. Now, before I derive the radioactive decay law, it is important to understand that radioactivity is a very different kind of a process. It is a very peculiar process. So for example, if you have a radioactive atom in a container, then you can never predict what is going to happen to that atom in the next 1 hour or 1 day or 1 year. The radioactive atom might undergo decay at some sort of a time period which you cannot calculate. However, if you have, let's suppose, 100 such atoms or 1,000 or 10,000 such atoms, in that case, you can make an approximate prediction as to what is going to be the number of atoms which remain after some time. What does this tell us? It tells us that radioactivity is a probabilistic process. That means you cannot make an accurate prediction for one atom, but you can make a very good estimation about a large collection of atoms. So with that in mind, let me tell you a very important experimental observation which is associated with radioactive decay. So one thing that is experimentally observed is that the rate at which the decay of any kind of a substance takes place, that means the number of particles that decay over a certain period of time, is directly proportional to the number of particles present in that point in time. That means the decay rate, which is basically given by dN upon dt, is directly proportional to the number of particles which is present in any given point in time. This quantity dN by dt is sometimes known as decay rate or activity, or you can also define this as the number of radioactive samples which disintegrate in a given period of time. Now, this is directly proportional to the number of particles present in any point in time. That means if a container contains large quantity of such radioactive sample, then the decay rate is going to be higher. If a container contains a very small quantity of the radioactive sample, the decay rate is going to be lower. And using this experimental observation, we can derive the radioactive decay law. So from this, I can say that the decay rate, the dN by dt, is basically equal to minus lambda n, where lambda is nothing but a proportionality constant. So lambda is a proportionality constant which is also known as decay constant or disintegration constant. Now I have introduced a negative sign here because the number of particles is decreasing with time. As the radioactive sample undergoes decay, the number of particles which existed becomes lesser and lesser with increasing time. If I did not introduce a negative sign, this equation would basically mean that the number of particles is increasing. However, in our case, the number of particles are decreasing, therefore I have used a negative sign. Here, of course, the decay constant will have some positive value. Now, if this is the expression, then I can interchange the terms between n and dt and come up with dN upon n is basically equal to minus lambda dt. Now, if I assume that at time t is equal to 0, let's suppose a container contains n naught number of radioactive atoms, and after some time has elapsed, the container now has n number of radioactive sample. Okay, so at time t is equal to 0, the number of radioactive sample is n naught, and after some time has elapsed, the number of radioactive sample remaining is n. I have written nt because n depends upon how much time has elapsed. So if I do an integration of this expression for this amount of time period, in that case, I can write dN upon n integration is equal to minus integration of lambda dt. So this happens over the time period going from t is equal to 0 to t, and initially at time t is equal to 0, the number of sample was n naught, and after some time has elapsed, the number of sample is n. So I put the limits as n naught to n and t is equal to 0 to t. This gets simplified to ln n upon n naught, which is equal to minus lambda t. All right, now because this is logarithm, I can basically write this as n is by n naught is simply equal to e to the power minus lambda t, which can be rearranged as n, which is the number of particles at time t, is equal to n naught e to the power minus lambda t. So this is the radioactive decay law which any kind of a radioactive sample follows. So n is the number of particles that exist in the container after time t, and n naught was the initial number of particles. As you can see here, this expression tells us that the radioactive sample will decrease in such a manner that it is going to show an exponential decay. And this exponential decay is going to be very much dependent upon time as well as the decay constant. So now decay constant is a constant which is not dependent upon temperature or pressure or density of the material, but rather it is a characteristic of the element which is decaying itself. To understand this process, to understand this exponential decay law, let's look at this particular graph. Now, as the radioactive sample contains n naught number of particles at time t is equal to 0, then this number of particles will decrease slowly in an exponentially decaying manner. If you look at this expression, you can say that this is very much dependent on the decay constant, because if the decay constant is a large number, then the decay is going to happen very fast. The number of particles is going to decrease rapidly. If the decay constant is a small number, then the decay is going to happen very slowly. The number of particles is going to change very slowly. Now, the decay constant is not the only parameter which tells us something about the characteristic of the radioactive species present. There are other parameters also which can tell a lot about the kind of radioactive sample present, and one of that parameter is the half-life. So the half-life of any given nuclear species or a radioactive species is defined in such a manner that it is the time period in which a sample decreases to half its original number. So that means if a sample decreases to half its original number, so if the sample has n naught number of particles initially and it becomes n naught by 2 after some time period, let's suppose t, then that time period is nothing but the half-life of that particular species. Quite simple. So in the half-life, the number of sample becomes half its original size. And if I apply this definition to that of the radioactive decay law, which we just now obtained, which was T is basically equal to n naught e to the power minus lambda t. So if t is the half-life, in that case nt is nothing but n naught by 2 by definition of the half-life, and this is nothing but n naught e to the power minus lambda capital T. So capital T half. So this T is the half-life. Now n naught and n naught gets cancelled and you are left with e to the power lambda T half is basically equal to 2, or lambda T half is nothing but ln of 2, or T half is equal to the natural logarithm of 2 is basically 0.69 divided by lambda here. So this basically gives us a relationship between the half-life and the decay constant of any nuclear species. As it should be obvious, if the decay constant is large number, the decay is going to happen very rapidly, so the half-life of the sample will be very less, and the opposite is also true. So what all of this means is that when the number of sample, let's suppose, decreases to half of its original value, so n naught becomes n naught by 2, then the time period it takes is 1 half-life. Okay, now if this number decreases to half its value, so if it suddenly becomes n naught by 4, suppose, now that is going to take another half-life. So this is going to be 1 half-life, another half-life, so this is going to be twice the half-life. All right, now if this becomes half its original half its value, if this becomes n naught upon 8, now this is again going to take another half-life, which is nothing but 1 to 3 times the half-life, so on and so forth. So half-life by definition is the time period in which a certain sample decreases to half its number of radioactive samples. Now sometimes the characteristic of a sample is basically determined by the half-life instead of the decay constant, but we can use both of these two different parameters in our problem solving. So for example, if there are two different kinds of radioactive sample, but let's suppose they have the same number of initial elements. So let's suppose one radioactive sample has a particular decay rate rate and another radioactive sample has, let's suppose, another decay rate. In that case, let's suppose the first radioactive sample has a decay rate, decay constant of lambda 1, and the second radioactive sample has a decay constant of lambda 2. By looking at this, you can say that lambda 1 is of course greater than lambda 2 because the decay of lambda 1 is happening faster. But by using this expression, we can already say that the half-life of the first decay species is less than the half-life of the second decay species. All right, so in a way, the ratio of the half-life of two different radioactive samples is inverse to the ratio of the decay constant of those two species. Now, there is another parameter which can also tell us a lot about the characteristics of a radioactive sample, and that is known as the mean life or the average lifespan of a radioactive sample. To understand mean life, I have drawn another diagram here. So let's suppose the sample has n naught number of particles, then after some time it has n number of particles, and after some time it has even less number of particles. Now let's understand something. These are all same kinds of nuclear atoms, okay? They are all undergoing the same kind of nuclear decay. However, the lifespan of each individual atom is different. That means the particle which undergoes decay in this lifespan has a shorter lifespan, and the particle that undergoes decay in this lifespan has a longer lifespan. So even though we are talking about the same nuclear species, some of these atoms will undergo decay in a very short time, and some of these atoms will undergo decay in a very long period of time. That means the lifespan of all of these atoms is not the same. So what is the average lifespan of all of these atoms? We can calculate the average lifespan by looking at the total lifespan of all of these particles divided by the total number of particles present. So this quantity is known as mean life or average lifespan. This is quite simply defined as the total amount of lifespan of all of the atoms present divided by the total number of particles. We can calculate this particular quantity by looking at this particular graph here, but I will not go too much into the calculation. Mathematically, this quantity can simply be written as the total lifespan of all the particles is simply the lifespan of any individual particle multiplied by dn, and this divided by the total dn here. So this is for time t is equal to 0 up to infinity, and this is from n naught is equal to 0. As it just so happens, this integration, the solution of this integration is basically coming out to be 1 upon decay constant. So basically the mean life, which is sometimes represented by tau, is inversely proportional to the decay constant. So the mean life is inversely proportional to the decay constant. It is kind of obvious because if the decay constant is large, the decay is going to happen fast, the average lifespan is going to be small. If the decay constant is a small number, the decay is going to happen slowly and the average lifespan of all the particles will increase. So this is another parameter which tells us how the radioactive sample is going to behave. We can also find a correlation between mean life and half-life. So we already know that half-life is basically equal to 0.69 divided by lambda, right? And 1 by lambda is nothing but tau. So here I can borrow this expression and substitute here to get t half is nothing but tau multiplied by 0.69. If I take the 0.69 and bring it to the left hand side, in that case this mean life is nothing but 1 upon 0.69, which is 1.44 multiplied by t half. So the mean life is basically equal to 1.44 times the half-life of the sample. That means the mean life is greater than the half-life of a given sample. Now what we have done till now is we have derived the radioactive decay law and also studied the parameters associated with it, namely the decay constant, the half-life and the mean life in this case. But as I already told you, the rate at which a radioactive decay happens is directly proportional to the number of particles present. That means if you have a large number of particles present, the rate at which the decay happens is greater. If you have a small number of particles present, the rate at which this decay happens is smaller. So we can also obtain another expression which tells us how the rate is going to change with time. This is known as the decay law with respect to activity. So as I already mentioned initially, the rate at which this kind of a decay process is happening is given by the decay rate. This is also known as the activity of a sample. So the activity of a sample is the rate at which the sample is undergoing radioactive decay. We can give it a very specific name also, which is known as the activity, and it is basically given by the symbol R. We have introduced a negative sign here because this is a decrease of the radioactive sample. So it's a negative number. So we want to get a positive value for this, so we have introduced a negative sum. Now this activity also changes with time. As the number of the sample decreases, the activity also decreases with time. So this is given as a specific quantity, and this quantity has a unit. So the unit of activity is becquerel, BECQUEREL, or BQ. So 1 becquerel is defined as 1 disintegration happening per second. Alright, so 1 disintegration per second is known as 1 becquerel. There is another unit associated with it, that is called curie. So 1 curie is equal to 3.7 into 10 to the power 10 disintegrations per second. So we can obtain the decay law for activity by looking at how this varies. So we already know that dN upon dt is basically equal to minus lambda n. The activity is directly proportional to the number of particles, and this is the proportionality constant or the decay constant. Now this is I have defined as activity. So this is nothing but R is equal to lambda n here, right? What is n? N we have already obtained from the decay law. It is nothing but lambda n naught, which is the number of particles present at time t is equal to 0, e to the power minus lambda t. Now I can define this particular quantity, the decay constant, multiplied by the initial number of particles as R naught. Alright, so R naught is the activity at time t is equal to 0. So this gives me an expression which is basically R is equal to R naught e to the power minus lambda t. So R here basically gives us the activity at any given point in time, and R naught is the activity at time t is equal to 0. So this is the radioactive decay law with respect to the activity. So till now we have discussed the radioactive decay law with respect to the number of particles that is changing, with respect to the activity that is changing, and also the other parameters associated with it. These kind of mathematical expressions helps us in problem solving. So let's try to solve a couple of problems using what we have just now obtained. So here we have a problem of radioactive carbon dating. So carbon dating is a method which is used to calculate the lifespan of fossils. And carbon dating is quite an interesting topic, and you can get problems of carbon dating because carbon dating is an application of the radioactive decay laws. So let's look at the problem. A sample of carbon-14 whose half-life is 5,730 years has a decay rate of 14 disintegrations per minute per gram of natural carbon. A fossil is found to have a radioactivity of 4 disintegrations per minute per gram of its present carbon. How old is the fossil? Now these kind of problems are quite common, and they are in fact very easy to solve, but students might have a little bit of a difficulty if they do not have the grasp on the radioactive decay law. So we can use this simple decay law associated with activity that we just now mentioned. So the decay law of activity that I just now obtained was R is equal to R naught e to the power minus lambda t. R naught is the disintegration rate initially, and R is the disintegration rate right now. Now by looking at the fossil, the disintegration rate initially was 14 disintegrations per minute. So R naught was initially 14, but now the disintegration rate has become 4. So R is basically equal to 4, right? So let's just put the values and see what we get. What is the time period? So if I put up the values, then I end up getting R is equal to 4 and R naught is equal to 14 e to the power minus lambda t, or e to the power minus lambda t is equal to 4 upon 14, or e to the power lambda t is equal to 14 upon 4, or lambda t is simply equal to ln 14 upon 4, right? Now we have not been given the decay constant, we have only been given the half-life. Here we can use the expression we obtained for half-life previously. So I can write, because half-life is equal to 0.69 divided by decay constant, so instead of decay constant I can write 0.69 divided by the half-life multiplied by time is equal to ln 14 upon 4. So the final expression then becomes time period is equal to the half-life, which is nothing but 5730 years, divided by 0.69 multiplied by ln 14 by 4. So the number of disintegrations initially was 14, now it is 4, and the half-life of the sample was 5730 years. So how much time has elapsed for the disintegration rate to go from 14 to 4? This is the amount of time period. And if you perform the calculations, the numerical calculations, then this answer simply comes out to be 10,358 years. So after 10,000 years approximately, the disintegration rate has gone from 14 to 4. So this is the age approximately of the fossil. Now here again we have a very simple problem. So given that the half-life of thorium is 1.4 into 10 to the power 10 years, calculate the time period required for 10% of the thorium to disintegrate. Now, this is a very simple problem. We can approach it simply by looking at the radioactive decay law associated with the numbers. So the number of thorium at some given time is basically equal to n naught, which is the initial number of thorium particles, e to the power minus lambda t, right? Now let's suppose initially 100% of thorium is there, and after some time 10% of thorium has undergone radioactive disintegration. So if 10% of thorium has undergone radioactive disintegration, how much remains? 90%, right? So if 10% thorium disintegrates, the remaining is basically 90%. So that means Nt is nothing but 90% of the initial thorium. So this is equal to 90 upon 100 of N naught. Quite simple. So let's put these values in the expression here. So I end up getting 90 upon 100 of N naught is equal to n naught e to the power minus lambda t. N naught ends up getting cancelled, and this, if I bring and to the left hand side, we end up getting e to the power lambda t is equal to 10 upon 9, which simply becomes lambda t is nothing but ln 10 upon 9. Again, we don't have the decay constant, we only have the half-life, but we can convert it easily, as you already know. So this can be written as 0.69 divided by the half-life multiplied by the time period is equal to ln 10 upon 9, which now if I take these expressions to the right hand side, the time period it takes for 10% thorium to disintegrate or for the total amount of thorium to reach 90%, its amount is basically equal to the half-life, which is 1.4 into 10 to the power 10 years divided by 0.69 multiplied by ln of 10 upon 9, which computes to exactly 2.1 into 10 to the power 9 years. So in 2.1 into 10 to the power 9 years, 10% of the thorium is going to undergo disintegration. So as you can see, problems of radioactivity are quite simple if you understand the decay law. And if you understand the other aspects of the decay law, for example, the decay constant, the half-life, the mean life, and also the decay law associated with activity. So that is it for today's video. I hope you have learned something about the radioactive decay law, and if you face some problem, some question of these kind of topics, then I hope that you'll be able to solve those problems. That's it for today. Thank you very much.